All right, let's take a look at this titration curve over here. So first of all, let's try to figure out what's in our flask. Let's see if we can at least figure out if it's an acid or a base. So remember, the initial pH is sort of what tells you what's going to be in your flask, an acid or a base, and it's less than 7. So we know we have an acid in here. And because we have an acid in the flask, we must be titrating it. Our titrant must be a base. So the base must be in the burette. Now I want to figure out the strength of these. And so what I'm going to do is I'm going to go straight to the middle portion of this little vertical region, and I'm going to take a look at the pH and equivalence. And it looks like we are above 7. So the pH and equivalence is greater than 7. Maybe we're about 8.5, something like that, but the pH and equivalence is greater than 7. So, and that seems to happen at about 50. So pH and equivalence is greater than 7 at about 50 mils. So if the pH and equivalence is greater than 7, that means we have a strong base with a weak acid. So we have a strong base, weak acid, titration. And the reason our pH is above 7 is because in a titration like this, you get a salt that acts as a weak base. So we might have, for example, some acetic acid reacting with a strong base over here. So this is our weak acid. This is our strong base over here. We're going to do a double displacement, and we'll get this salt over here, CH3COONA, this sodium acetate, plus some water. And so this is our salt, and you'll notice that this Na does not have any effect on the pH because it's the salt of a strong base. But this acetate, CH3COO-, is a salt of a weak acid. Therefore, it acts as a weak base and gives us a pH above 7 in the end in our titration once we've reached the equivalence point. So we figured it out by just looking at the equivalence point. Let's just take a look at the characteristics of this titration curve. Similar to the strong acid, weak base, we start off with a sharp increase because we're adding that strong base and it's to a weak acid. But you'll notice that eventually it slows down. And when you slow down, what starts to happen there is you have slowed down because you have created what's called a buffer region, where you have an equilibrium that's been created with your conjugate acid, with your weak acid and your conjugate base. So plus H2O here. And you get this CH3COO- plus H3O plus. And so you've set up an equilibrium between your conjugate acid and between your weak acid and your conjugate base. And so now what's happening is you're minimizing the change in pH as you add base to this buffer system here. So as you add your base, you're essentially going to be reacting with the acid to prevent any change in pH. And that's why this slows down drastically here, because you've created a buffer in the buffer region. But as soon as you added enough base and you've reached the buffer limit, then your pH starts to rise rapidly again, and you're in that middle region there for your equivalence point once all your base is reacted with the acid. But if you continue adding base, then you're going to go in the overshoot, and at that point your pH is really just determined by the concentration of the strong base, because you've already wiped out all of the weak acid that was there. So this is a titration curve for a situation of a strong base with a weak acid. How is that different from the other titration curves we've seen? Well, here we have a titration curve where we have an equivalence point that is less than 7. So I look at that and I say, oh, this is an equivalence point that's less than 7. So when I see an equivalence point that's less than 7, what that means is that I must have had a strong acid and a weak base instead. And you'll notice this titration curve is a bit different. We start off over here with a pH that's higher than 7. So what that means is that since we're monitoring what's in the flask, whatever was in the flask must have been the base. And so we have a weak base here. And then in the burette, because you titrate with the acid, in the burette we must have had our strong acid. So this could have been, for example, HCl, and this over here could have been NH3. And so the reason that this situation here, we have a pH that's less than 7, is because when you have a strong acid, weak base titration, you get a salt that is acidic. So for example, I'm going to do a reaction here. I'm going to do NH3 plus HCl, and I'm going to show you the salt that's made. It's NH4Cl. And that didn't show water. I just kind of simplified by writing NH3 here. But the idea is that that Cl will not have an effect because it's the salt of a strong acid. So it won't want to go and hydrolyze water to make HCl. It won't do that. But this NH4 plus over here is a salt of a weak base. So this acts as a weak acid. So that acts as a weak acid. And that's why our pH is less than 7. And you'll notice that we have similar profiles. So even though we started with the base in the flask, it doesn't matter. When we first add the strong acid, you have a sharp decrease in the pH because you're adding strong acid to a weak base. But then eventually it slows down because you have this buffer region that has formed. And that buffer region over here is formed because you have an equilibrium that happened between your weak base that you had in your flask and its conjugate acid. And so what happens is as you add the acid from the burette into the flask, this little equilibrium system over here is going to absorb the acid and prevent change in pH. But that has a limit. So eventually you'll add so much strong acid that you've kind of broken the buffer, and then your pH starts to decrease drastically again, and you get this vertical portion, and in the middle you'll find your equivalence point where all your acid has reacted with your base. And then if you continue adding beyond that, then your pH is going to be determined by the strong acid because you've already wiped out all the weak base. So now your pH is just very, very acidic because you just keep adding more and more strong acid. But the whole point is that you want to aim to get your titration to end close to that equivalence point within the vertical region. But the main idea as well is that we were able to identify what was in our flask based on the starting pH and the type of titration, strong acid, weak base, based on the fact that we had a pH that was less than 7 at equivalence. And then we saw that for these strong, weak type of titrations, you have buffer regions that are created because you have a weak acid and or a weak base and a conjugate. And a buffer is really created when you have some kind of weak acid conjugate base or weak base conjugate acid equilibrium that sets up so that way the system can absorb any acid or base that you might be adding to it. That buffer region doesn't really get created in the strong acid, strong base situation. Let's take a look at that and why. So in this situation here, I know right away that this is going to be a strong acid, strong base titration because the pH is equal to 7 at equilibrium. So the pH is equal to 7 at equilibrium. And so that means I have a strong acid, strong base titration that's happening. And the reason for that is because why is the pH 7 at equilibrium, or not equilibrium, sorry, at equivalence point? It's because when you do this reaction, you get a salt that's produced, and that salt that's produced is a neutral salt. This is a salt of a strong base. This is a salt of a strong acid, so they won't hydrolyze water to go back and reproduce acids and bases. So that's why our pH is 7 when you have a strong acid, strong base titration. Now, what do we have in our flask to begin with? Well, in our flask to begin with, we must have had an acid because the pH is less than 7. And that strong acid is HCl in this case. And so what that means is that in our burette, we must have had the base, the strong base, which is NaOH. Whoops. And as you add drop by drop by drop of base to the HCl, the pH will go up. And it's a fairly constant increase, but it's slow at first, not because of a buffer region, just because you have a lot of acid and not a lot of base. And eventually, as you add more and more and react with more and more and more acid, and you get rid of more and more acid, your pH will start to rise much more quickly. And within this sharp region in the middle, you'll find your equivalence point, and that's where you want to aim for, somewhere in here. But as you continue to rise beyond that, you're overshot, and now your pH will be determined by your base because you've essentially wiped out all your acid, and you just continue adding base. but there's no buffer region here, because when you have a strong acid, strong base titration, let's say we look at the strong acid in the flask, it's not going to set up an equilibrium. Remember that strong acids and strong bases, they don't set up equilibria, right? Because they go into one direction mostly. So because they don't set up equilibria, they can't really go back and forth to buffer or to cancel out addition of acid and base like a buffer system could. It could absorb some base, go back and forth to minimize the change in pH. But in this situation here, since you can't go back and forth, you can't really minimize the change in pH using a buffer system. So a buffer system, buffer region, this fancy profile here is really only truly created when you have the strong, weak combination situations. So we didn't really go over buffer in a lot of details. There is an extra lesson you can take a look at to see how you can set up a buffer in some more detail. You can go ahead and take a look at that. But the main point here is that this was an overview or a summary of the different types of titrations we've seen. And we just went to analyze how we could figure out what type of titration that we're looking at using the pH at equivalence. So after you've done all your calculations, or while you're doing calculations, it's important that you take a look at these titration curves, and maybe you can sketch some to reflect the type of titrations that you're doing in the different questions.